All right, we're going to look at some rates of change here today. We've looked at before if you have a position function, which gives the location of an object in terms of the time, then if we found the rate of change of that, that would be its velocity. So the first derivative of position ends up being the velocity function. If you find the rate of change of the velocity, like how much is the velocity changing, that's a description of acceleration. So the velocity, or the derivative of the velocity, or the second derivative of our position function ends up being our acceleration. So let's look at an example. We're going to look at this. It's going to be the same information, just different things we're going to be finding from this with using derivatives and other math stuff we know from throughout the year. So this one gives us the position of a particle given by this equation. So S, or f of t here, is equal to t cubed minus 6t squared plus 9t, where t is measured in seconds and s is in meters. Find the velocity at time t. So what they're looking for here is what is the velocity function. And we can find that our velocity function here should be the derivative here for this function. So if we find the derivative, that should give us what we're looking for. So just using our little power rule here, we got 3t squared minus 12t. And then our last one derivative of that would just be 9. So this now gives the velocity at any time t. We can put in any time and find the velocity of this function up. And the next part of this question does ask us to find then a couple of the velocities. So what makes it easy now is if we take that velocity function we just had and we plug in any time we got that. So let's do 2 here. What is the velocity at 2 seconds? Well, just plug in 2 for all the times, and we should get it. So if I put in 2 for that first one, we make sure you do the squared part first. 2 squared is 4, times 3 would be 12. 12 times 2 is 24, so we got 12 minus 24 plus 9. If you subtract those, you get negative 12 plus 9 would be negative 3. And this would be measured in meters and seconds here, so it would be meters per second. What does the negative indicate on this? The negative indicates a direction. So if we're moving up and down, that would mean it's moving down. If we're moving left or right, that would mean it's moving left, depending on which direction we're moving there. Why don't you pause the video and see if you can find the velocity at 4 seconds now and see what you get. All right, let's see if hopefully you've had a chance to try that here. If you put in 4 now for t, we get this right here. Simplifying, you should have got 9 meters per second positive, which means at 4 seconds it's moving in the opposite direction than it is at 2 seconds because it came out positive. All right, let's keep rolling here. Part C, when is the particle at rest? Well, if we have our velocity equation that we've been using the last 2 problems here, and we want to know when it's at rest, what that is telling us is at rest indicates velocity is 0. And so what you want to do then is plug 0 in here for the velocity and solve this out. So we're trying to find a when, we're trying to find this t over here, what time does that happen at? So we got to figure out a way to solve that. It's a quadratic, so our choices here to solve this would be to use quadratic formula, which will definitely work, or possibly factor this one. To factor it or see if it's factorable, let's first, looks like we could factor out a 3 there. So I'm going to divide everything by 3. If we did that, we get t squared minus 4t plus 3, dividing everything by 3. So just went through here and divided everything by 3. Does the rest of this factor? It does look at it like it is going to factor here. Looks like it factors to minus 3 and minus 1. And so the times for which this is at rest, if you put these now equal to 0, to solve would be at 1 second and also at 3 seconds. It's at rest. So those would be the two times when this particle is not moving. Part D, when is the particle moving forward? That is in a positive direction. So what we want to do for this now is look at our velocity and look at it kind of in this factored out form. And in the factored out form, we had that it was 3 times t minus 1 and t minus 3 when we had factored that. And see if we make a little diagram here, we know at 1 and 3 seconds it's at rest. So what's it doing in between and outside of those? So let's put in some test points here. Like what if we put in 4 for the time? Well, at a time of 4, this is going to come out positive. 4 minus 3 is 1. 4 minus 1 is positive 3. Our 3 is positive. If we multiply 3 positives, it's moving in the positive direction anytime after 3 seconds. If we put in a number in between like 2, which we've tested already, we know this comes out negative because we got positive 3. 2 minus 1 is positive, but 2 minus 3 comes out negative. If we multiply 2 positives and a negative, that's going to move in the negative direction. If we put something less than 1, like 0, this is going to be a positive 3. That's negative, but multiplying those, that becomes positive as well. So when is the particle moving forward? It would be moving in the positive direction from 0 to 1 seconds and also 3 seconds onward. It would be moving in the positive or moving forward there. All right, next they want us to draw a diagram to represent the particle of this motion. So we're going to kind of combine what we know here onto a graph. So if we make a graph, and we want our major points on here. So 0, 1 we want on there. 3 is also a major point because we know at 1 and 3 it's stopping here. What does this look like? To get some points here, we know if we put 0 in at time of 0, looks like if we were to just put 0 in for all these, it is going to be at 0 when we start. What is it at like 1 and 2 and so on? Well, we got a couple of those points already if we scroll back here to some of the previous ones. Sorry, I guess that's at velocity. So I guess we don't have any more locations, but we could plug them in if we wanted to find some of those out. But we do know at 1 second and at 3 seconds, whoops, wrong thing here. All right, at 1 and 3, that it's the velocity is 0, meaning we're going to have a change of direction at those. And then we know it's moving positive or forward or positive slope between 0 and 1 and negative between. So my guess is it's going to go up. At 1, we know it's going to change direction because for a moment here it's at rest, meaning our rate of change or our slope is 0. It's going to decrease till 3 seconds. And then at 3 seconds, again, we have a change of velocity here. So it's got to be that. And then it's going to increase again or move in the positive direction. Okay, so let's graph that out and see if that makes sense. So I type this in here. You can see the equation I got typed in. If we hit graph, does our graph look pretty similar to that one? Looks like it, yep. So it increases, decreases, and then increases again. If you wanted to get a little more specific, we could fill in the position over here by plugging in some different times. But this gives us a decent representation, which they wanted, of the motion. All right, next part, F, find the total distance traveled during the first 5 seconds. Okay, so what we can't do on this one is just take our position function up here and plug in 5, because plugging in 5 will tell us the location at 5, but it doesn't tell us how far it's traveled. So what we got to do is look at the different sections here. If we go back to the graph we just looked at, where is it traveling in these different sections? So the places we're going to need to figure out is, what is it doing from 0 to 1? Because it's moving forward in that one. We also need to figure out how far does it move between 1 and 3, because there it's moving a different direction. And then we also need to figure out how far from 3 to 5, because we ultimately how far is it traveled between 0 and 5 seconds. So we're going to have to split this up in intervals in order to do this, because it's changing direction. If we just took where it's located at 5 and subtracted where it was located at 0, that gives us something called displacement, which is something that you can find, but it's different than distance traveled. So what we want to do here is find out how far has it traveled from 0 to 1 seconds. We also want to find out how far has it traveled from 1 to 3 seconds, and then also from 3 to 5 seconds. And in order to do these, we want to subtract. So we want to know for this one we're going to have to take S of 1 minus S of 0. For this one, we're going to have to do what's S of 3 minus S of 1. And for the last one, we're going to have to take a position at 5 minus the position at 3. Okay, so it looks like we do need some of these positions. So let's find those out. There's a quick way you can do that with the calculator, and that's to use the table. So if you already got this function typed in, if we go to the table, that should give us with the different times where the position's at. So if we look here at 0, the position is 0, so that ends up being 0. If we go back to our table at 1, the position is at 4. And you could also get that again by just plugging 1 in for the t's here. So it looks like during the first 4 seconds, this moves 4 meters. Okay, the next one, we already have our position at 1 is at 4. Let's find our position at 3. So our position at 3 here ends up being 0. So this ends up moving -4 meters, and again the negative indicates just the direction, so it's moved 4 in the opposite direction. And then our last one here, position at 3 is 0. What's our position at 5? So if we go back to our table again, scroll down here, it looks like at 5 it's at 20. And so here it's moved 20 meters back in the positive direction. So how far has it traveled total? Well, what we want to do now is take the positive direction of all these and see what they are. So we want to add together basically like the absolute value of all these. So we want to take what's the absolute value of this, which would be 4. What's the absolute value of this, which would also be 4. And what's the absolute value of this, which would be 20. So if we add all those together, we get the total distance traveled. So total distance traveled here would be 4 plus 4 plus 20, or 28 meters. So during those first 5 seconds, this particle moves 28 meters. Okay, part G, find the acceleration at time t and after 4 seconds. So remember, our rate of change of our velocity here is our acceleration. So here's our function for s up here. We got our function for v, which we've been using the last few problems, which is this. And now we're going to find acceleration. So acceleration is going to be the first derivative of the velocity or the second derivative of our position. So we want to find what's the rate of change of this one right above us. That's just using our power rule again. So bring down the 2. 2 times 3 would be 6t. Bring down our 1 on the next one, so minus 12. And the new power would be 0, so just negative 12. And then our constant here, derivative of a constant, derivative of 9 is just going to be 0. So that would be our acceleration function right here. Okay, and then they want us to also find what is the acceleration after 4 seconds. So the acceleration after 4 seconds here, we're just plugging in 4 for the time, and we should be able to find that out. So this would be 24 minus 12, or acceleration is going to be 12, and this is our rate of change of velocity. So remember, our velocity was measured in meters per second, and this would be again per second, and so it's meters per second, or another way to write that is meters per second squared is often how you see acceleration right there. All right, so that would be our acceleration after 4 seconds. All right, graph the position, velocity, and acceleration functions from 0 to 5. Okay, so for this one, they want us to graph all 3 of them kind of on the same graph here. So we have already before graphed our position one out here. So let's recreate that. Okay, so our position one looked like this. It started at 0, it went up, down to 3, and then it went back up again. So that was our position one. Let's graph our velocity. So we'll go back to our calculator here. Let's type in now our velocity function that we've been using. So our velocity function was 3x squared, and then minus 12x, and plus 9. So if we graph this one, here's now our velocity graph. So it's at 0 here. We could, if we want, we could get a table to kind of see, but it looks like at 0, the velocity is 9. So it looks like it's a little bit higher, maybe up than what this one is. So for this, it starts up here. Okay, from the graph, you can see when does it achieve of velocity of 0 at 1. Okay, and the reason that is, again, remember what's our tangent line there? 0. So that should make sense. Also, it's going to have another 0 here because the velocity is 0. Down here, it got negative, and then it went back up. So our velocity graph looks something like that. Okay. All right, next. Finally, they want us to graph what is the acceleration. Let's try doing this one without graphing on the calculator first and see if we can get it, and then we'll check and see if the calculator's right. So acceleration now. Let's just do it based off the graph. So remember some things we talked about here. What's the tangent line here? It's 0. And so when we're graphing this out, then if we know that tangent line is 0 at 2, that means the acceleration should be 0. What kind of acceleration do we have here? Well, we're looking at the slope. What kind of slope do we got? Positive. So the slope here should be positive. And what kind of slope do we got on this side of 2? It's negative. So slope here should be negative. So I'm guessing the blue graph's going to look something like this. Let's check it out and see what we get. So let's type in that third equation now. So if we type in what we got for the acceleration, which was 6x minus 12, and hit graph here. There's the picture, and yeah, it looks like our picture, maybe I should have had this slanted a little bit more, but you can see it is at a straight line here, looking like that. So that's an example of the graph. You're always looking for those slopes. So if you're asked to do one of these, look at what the slopes do it. If we go from like our red one to green one again, slope here is positive. So this line's always above the x-axis. Slope is 0. We had a point at 0 on the green graph. Slope is negative. All these points were below. Slope was 0 right here, so we had a point at 0. Positive slope, so the green one's above the x-axis. So those are the type of things you're looking at when you're asked to graph these out. Okay, keep going here. When is the particle speeding up? When is it slowing down? So when doing these ones, things are said to be speeding up. That's going to happen anytime velocity and acceleration are moving in the same direction. And so in other words, they have the same sign, positive or negative. It's going to be slowing down when velocity and acceleration are moving. Writing's going bad here. Moving in opposite directions. And so then, similar to what we had before, that means you're going to have opposite signs. All right, so let's see if we can do this one. We've already before come up with that little map we had, or number line with velocity. So when we did this before, when we had our velocity, we figured out at 1 and 3 was when the velocity was 0, and we had that it was positive, negative, positive. Now we're going to do the same thing with acceleration and see what our acceleration one looks like. To do that first, though, we got to see when is the acceleration 0. So our acceleration equation again came out to be that acceleration was equal to 6t minus 12. Let's put 0 in for our acceleration and see where we get acceleration 0. So if we add 12 and divide by 6, looks like at 2 seconds our acceleration is 0. So on this problem here, what we're going to do then is at 2 seconds, we're going to have that be our marker. So what is it when we're bigger than 2? When our time is bigger than 2 seconds and less than 2 seconds, what kind do we get? Well, we already found what the acceleration was at a time of 4. That came out to be positive 12. So when we're bigger than 2, we know it comes out to be positive. What about if we picked something less, like 1? Well, if you put 1 in there, you're going to get negative 6. So when you're less than that, it comes out negative. We can also see that from our graph here. When we're less than 2, we got negative points there. Okay, so now we want to look at when are these the same? When do we have signs that are the same? So if we were to put this on the same graph, what would we see? When do they match up? So I'm going to make a one here that has all three of these times on. So when I use some different colors here too so we can see this better. All right, so in here, in this range, our acceleration is positive all throughout here. Here it's negative. Our velocity, what we got for that is that it's positive here. Between 1 and 3, it's negative. And after 3, it's positive. So when do we have the same signs here? We get the same signs moving in the positive same direction. So when it's speeding up here, same sign, that's here and here. So it's going to be speeding up between 1 and 2 seconds. And also it's going to be speeding up in the opposite direction, 3 on. Speeding up. Okay, when is it slowing down? Slowing down is when you got opposite signs. That's when we're slowing down. So opposite signs are in these two areas. So it's slowing down here between 1 and 2 seconds it's slowing down, and also slowing down between 2 and 3 seconds. Okay, so that's when it would be slowing down. And remember, that should make sense because what do we know happens at 1 second? It's at rest, so it's got to be slowing down before it's at rest. And same thing, we know it's at rest at 3 seconds, so it's got to be slowing down before it comes to rest at 3 seconds. So those would be the answers there. All right, you're going to now try some of these out on your own.